Okay, so let me quickly repeat for the Zoom people. Today I'm gonna explain, yes, sorry. I'm gonna explain a more geometric approach, and it's used Fock and Goncharov, that associates an algebraic torus C star to the n to every seed, and we're gonna construct a variety or a space, a scheme out of this. So for every seed we encounter, we're gonna have this algebraic torus, and we're gonna take the union over all of them. In order to build a scheme, I only need to tell you now how to glue two tori in this atlas. And this formula should look very similar to what we've seen yesterday. It's exactly the mutation formula. So when I go from one torus TS to the torus associated to the seed that I get by mutating in direction K, then this is what I do on the coordinate level. Yeah. So this is the mutation describes the pullback of the birational map between the two tori. Okay. Any questions? Great. Okay. So let's look how this looks for in the Grassmannian 2-4, or to make my life a bit easier, I'll be working in the affine cone of the Grassmannian. We already observed the number of vertices in a quiver of this cluster algebra is the dimension of the affine cone rather than the Grassmannian with like one extra face in every Plabic graph. So I get two algebraic tori. The coordinates are exactly in the Plucker coordinates of the two seeds, my two positivity tests. And well, the transition map between the two is exactly given by expressing what comes in the place of the coordinate of the Plucker coordinate 2-4 in terms of the others, right? Using my Plucker relation. Okay, so yes, this approach is very nice. It's very scheme theoretic. What I get out of here is not a variety. It's an algebraic scheme. But it comes with the advantage that I can change my base field, right? So I would be usually working over the complex numbers maybe, but I can change my base field by simple base change. And then looking at these transition functions and also remembering that we have the positivity of the Laurent phenomenon, which essentially tells us if I want to glue two tori that are further apart in my atlas, then also the transition map between these two will be completely expressible in terms of positive Laurent polynomials. So in no transition map, wherever in my atlas I have a minus sign appearing, meaning I can also work over semi-fields, right? So I don't need the operation minus, so my field doesn't need the operation either.
But in this example, if we choose that the base field of the scheme is C, is there a way to get, like, what would be the equations that would cut out the cluster variety, for example, GR?
So yeah, okay, this is not a variety. This is contained in the Grassmannian, and then you have the equations, but we cannot cut this out just by equations. Like, it's not as a risky closed set in projective space. But it's open inside, in this case, open inside of the Grassmannian, or it's affine cone to be precise, yeah. And also in general, remember, like, we have a short list of examples where these cluster structures, where the cluster algebras have a finite list of seeds. So in general, this is a huge atlas, an infinite atlas. It is redundant. Like, for example, for the Grassmannian, even the infinite type Grassmannians, we only need a finite list of tori to cover it, at least this open part. And those are the tori corresponding to Plabic graphs. But still in the cluster structure, we have like the zoo of other tori.
Well, can you explain the subscripts? I didn't quite understand what you said about the subscripts for the C star 5s.
Oh, so these were the seeds or the cluster variables of the two seeds that we found, or the positivity tests. And
you're saying those are our variables for.
Yeah, we choose them as coordinates, as local coordinates for the torus. Yeah. Yeah. So each one of those is a chart to the affine cone of the Grassmannian. It gives a parametrization, a local parametrization.
But they do cover everything.
They do cover it, yes.
So the Grassmannian gives you an embedding of this affine, right?
Well, no, right? I mean, there's many points missing in this union in comparison to actually the Grassmannian. None of my Plucker coordinates can vanish here.
Then the gluing also.
In
Oh, I see.
also, yeah. So everything is non-zero.
It covers the puzzle.
It it covers the big open cell inside the Grassmannian where no coordinate vanishes. Yeah. Okay. Great. So right. So let's see where we go. If we can work over semifields, let's explore that a bit. Two semifields probably of interest to this audience. Well, one definitely of interest: the positive real numbers. So this tells us that every cluster variety has a positive part. We can just pass through this, we do the base change working over positive real numbers. We have a positive part of a cluster variety. And we can also work over tropical semifields, be a bit more exotic. So my favorite tropical semifield is this one, the integers with the operations taking maximum and sum. So if we do that, really what we have to figure out is what am I actually gluing? And Fock and Goncharoff tell us, and it's not too hard to check, that, okay, if I take the tropical integer points, it's what I call it, if I work over this z-trop, of a torus chart, it will actually just be its co-character lattice. Okay, so instead of gluing algebraic tori, I will be gluing co-character lattices of tori. And well, what are the transition maps? If I have two co-character lattices, well, I just tropicalize the map that I had before, right? All I have to do is change my base field, the operations adjust accordingly, and this happens to the transition functions if I replace taking the sum by taking the maximum and multiplication by taking the sum. So this is a piecewise linear map from a lattice z to the n plus m to z to the n plus m, right? All my tori are isomorphic. And then the Fock-Goncharoff tropicalization of a cluster variety is take the union of all these lattices and identify points in one lattice with another lattice if they're mapped to each other under this kind of map or concatenations of this map. Right? So in this case, I just have several copies of the same lattice, and a point in my tropicalization is like a class of points, one in each lattice, with the condition that these maps map them to each other. Right? Okay. So here's an interesting thing. These maps are piecewise linear. So every piecewise linear map gives me a complete fan in the lattice where it's defined, or the real vector space that is its ambient. And if I consider all these transition functions and their concatenations, I get lots of piecewise linear maps, lots of fans, and I can consider their common refinement. And the tropicalization, this abstract union of lattices, turns out to be the support of the fan that I get to doing the common refinement of all of these. Okay? And it's defined well in the real. The ambient space is the real vector space. Ambient of my lattice. Okay, so this is a fan that appears a lot in cluster algebras. This is one way to get to this fan, but this is also known as, or it's a fan realization of the exchange graph that encodes the combinatorics. So the maximal cones in this fan correspond to my seeds. Two cones are adjacent. If they are related by mutation, the corresponding seeds are related by mutation. It's a simplicial fan. It is infinite if my cluster algebra is of infinite type. It is complete if and only if my cluster algebra is of finite type. Yeah. Okay. Any questions?
And like the normal fan of some like mutation polytrope?
If you're in finite type, yes. So if your cluster structure has finitely many seeds, then this will be the normal fan. And you will have different realizations of it. I mean, here I'm being a bit vague because this is a tropical space, an abstract tropical space. This lattice or this identification actually loses a bit of the lattice structure because in the tropical space we don't have what are we missing? We have, this is an end torsor, so we can still dilate things, but we can no longer add in this lattice. So this looks like a lattice. It's as a set, it's isomorphic to the lattice, but we have less operations. And here also this this fan, yeah, once we fix a seed, we can realize it as an honest fan, and then we can ask for the polytope that is not. Okay, good. Okay, so then let's run through the Grassmannian and compare.
There's one more question.
Yes. Oh yes. So
Just the last slide. These are all bands in NS or NS prime.
Sorry. As a so in this case, so whenever I really want to talk about a fan, I choose one fixed initial seed.
Good.
In this case, it would be S.
Okay.
And then I pull all the linear regions back to that real vector space or that lattice NS, and look at it as an honest fan there. So there's always a choice of whenever I talk about a fan, I chose one seed and I use this seed as giving me coordinates to the real vector space or to the ambient, to the lattice, and I express everything there. Okay. Yeah. So let's see. And then so I have the linear domains. I have them in S, right? Sorry, this is a typo. Yeah. Yeah. Because the domains of linearity are in the C corresponding to S. My maps go in the same direction. Mutation from S to S prime and the map between the lattices. Yes. Yeah. Good. So let's check the example of the Grassmannian. It's very small. Okay. Okay. So we said in the Grassmannian 2-4 or the affine cone, we have these two algebraic tori. So my fan sigma S would have two cones, one corresponding to each. And that's one way now how I can think about tropicalizing at least this open part inside of the affine cone of the Grassmannian. Right? This is the Fock-Gonchar way to tropicalize things. On the other hand, we also know about the Plücker embedding of the Grassmannian, and we can tropicalize that ideal. And this is another way to tropicalize an open part inside of the Grassmannian. And we get, well, the tropical fan in R6. So here's a description of how these look like in my coordinates. Sigma 1, 3, the seed corresponding to this one. If you would sit down and tropicalize the mutation map and see where are the linear regions, you would read off that this defines the cone. And here, similarly. So in the tropicalization of the Plücker ideal, we have 3 maximal cones corresponding to, like, always deleting one of the 3 monomials in my Plücker relation when I pass through the initial. And these are the 3 cones. And the map that I have this map between these 2 spaces that is doing what? Well, on this side, what did I do? Yeah, okay, so this is the parametrization map. Right here I have coordinates corresponding to one of the seeds. I fixed the green one, the seed that contains P13. So I've expressed everything in terms of these coordinates, and I can map it over to this other real vector space, or even I can have this as map from C star to the 5 to C6. And here I have one more coordinate that is just expressing the missing Plücker coordinate in the variables I've chosen. And this map, so here I wrote down the tropical version. I also have the version over the complex numbers, and it sends this fan into, or these 2 cones into these 2 cones. So an observation, if you can check here, is that the image of my fan sigma S here is the positive part of the tropicalization on the right side. So I'm hitting 2 of the 3 cones. Okay. And yeah, this procedure works in general. Are there any questions on the example, what I'm doing?
Here, the positive coefficients really make sure that there can't be cancellation, right? that you can just tropicalize this map safely.
Yes, yeah, exactly. The whole contour of tropicalization relies on the fact that none of my transition functions have any minus signs, and yeah, that it makes sense to evaluate everything in positive real numbers, tropical fields, whatever. Yeah.
Just to check, I'm saying the thing on the left is the domains of linearity for the map that expresses the new Pluger coordinate and the old Pluger coordinate.
Yes, it's here. Should be, right? If I didn't do any mistakes, this should be the domains of linearity. This gives me the domains of linearity, right? Either this term wins or this term. So those are the two inequalities. Yeah.
Can you mention a bit more, like, why do you get the positive part in general? Like, on the left-hand side doesn't seem to be having any notion of positivity, it's just reals.
No, the left-hand side is always positive.
Ah, okay.
The left-hand side, everything is always positive. Yeah, so you really don't have another chance. Yeah. Okay. I mean, yeah, if you want.
Sorry, it's always positive, you mean the U's are always positive?
So whatever cluster variety you have here, it lives inside some other ambient space, let's say variety, defined over the real numbers. Everything's nice. This always has non-trivial positive real points.
Yeah.
So yeah, so this so you know that this cluster variety lives completely inside the positive part of its ambient space. And then the same phenomenon. Okay, there's a bit of things to check. But the idea here, okay, to prove this in general, what do? You consider the degenerations of your original space here. If you're in the positive tropicalization, you know that these degenerations also degenerate the real positive part of your space. There's a theory of degenerations constructed from this side, and they also fulfill this property that they degenerate the positive real part. And then you have to just match the two sides and check, like using valuations, you check that you have the same degenerations on both sides.
So can we think of the U and J as valuations of some positive Laurent?
Absolutely. Actually, yeah, this the integer points here, you can think of them as being images of evaluation of elements of the cluster algebra. That's exactly the thing.
Question from Lawrence on Zoom. Can you say once more which two of the three codes we are mapping to?
So we're matching the ones of same color. So the green one here, U12 plus U13 greater or equal U14 plus U23 goes to the green cone here, where you can see really, I mean, if the variables U and V have the same index set, we really just map them onto each other. The only extra variable we have here is W24, which is this expression. And yeah, so if I'm in the green cone, then I know U12 plus U13 is greater. So the maximum is taken here. So W24 takes this value, U12 plus U34. And these, and then, wait, isn't it?
-2.
So now I wonder if I do I have a pipe or something, and U13. Minus U13, sorry. Okay, yeah, it's good if you can read the slides. Hopefully better than me, right? So W13 plus W24, if I start with a point in the green cone, becomes U12 plus U34. Because this one wins the race in the maximum, and then I subtract U13, which equals W13, and that's how I identify green cone with green cone, pink cone with pink cone, and nothing hits the third cone. Okay. Great. So let me give you the general statement here, or like one simplified general statement. If I start with a finite type cluster algebra, and I consider, and it's of rank D, so n plus m is D now, and I consider the set of all its cluster variables, 1 to capital N is now the complete set of cluster variables, not just for one seed. So that my cluster algebra is actually isomorphic to this quotient of a polynomial ring. This ideal I always contains the exchange relations. Well, we had this question, I think, yesterday. It's a bit bigger. It's a saturation of the ideal generated by exchange relations. And then the vanishing set of this ideal contains the cluster variety, right? This is now an honest algebraic affine variety. And my cluster variety sits inside of there. And now what do? I fix a seed, because I always like to work with coordinates. I fix one seed. Fixing a seed gives me coordinates, local coordinates on this cluster variety. I can embed it then into the vanishing set of this ideal. And what's that embedding? Well, the variables that I fix, they just go to themselves. So in this list, these are the coordinates of my affine space, right? So the first D are exactly my seed, just identically map them there. And the rest here, those are these positive Laurent polynomials for all the other cluster variables expressed in the seed I've chosen. Yeah, so this is an embedding of the cluster variety into this affine variety, compactification of it. And then the statement is that what we observed on the slide before works in this generality. So if I tropicalize this map, meaning I get a map from R to the D to R to the capital N, then the image of the tropicalization, the Fock-Onshov tropicalization of the cluster variety, this fan that we computed, is the positive tropical part, the positive tropicalization of the idea. Okay? And yeah, so that's it.
So we're filling the blanks, we makes a cone.
Cone goes to cone. There's a piecewise linear map that respects the fan structure of the two. Okay. Great. Okay, let me just pause for a second if there's any more questions or doubts. Otherwise, from here, we're going to move on to what I initially announced would take place in this lecture. Okay.
Is this supposed to be the G vector fan? Or
Yes, sigma is the G vector fan. Yes, absolutely. Okay, good. So in case you got lost or bored or you don't care about tropicalization, you can come back now. we're gonna change topic and talk about another cool thing that you can do with cluster algebras. And we're gonna get back into more combinatorial parts of the story. So here's a definition that you can find in the preprint book of Lauren and Sergey, Fomin and Williams. That's how, or in general, in cluster algebras, if you would think of them as a category, it would be nice to know some notions of maps between cluster algebras or what are cluster subalgebras. And it's always a bit tricky to talk about these things because you would really like to have compatibility of the combinatorics that you associate to the different cluster algebras. So here's one approach to make sense of a notion of a subcluster algebra. Lots of words, but I promise the intuition is quite natural because you've already been exposed a bit to the combinatorics. So what do I do here? I start with some seed for some cluster algebra, and I partition the vertex set of the quiver, so I partition the set of cluster variables. And I do that in such a way that, and then I choose a subquiver, Q prime, that is obtained from the big one by deleting one of the two vertex sets. So it's a full subquiver, just get rid of some of the vertices. And then I can consider the subquiver with the corresponding collection of cluster variables. And this is called a restricted seed of the big one, right? I'm just getting rid of some of the vertices. And this operation of restricting commutes with mutation. So it gives me, if I now start mutating only in the subset of vertices, it's giving me a sub-pattern of the big one. And so it makes sense to talk here about a subcluster algebra, right? If I construct a cluster algebra from this smaller restricted seed, it will always be contained in the corresponding seed of the big one. So this is what we call a cluster subalgebra. Yeah. And okay, so the point of this slide is to get to an interesting example of cluster subalgebras where the big quiver will correspond to the cluster algebra of a Grassmannian, and the small quiver will surprisingly correspond to partial flag varieties. Yeah, so in general, if you think of Grassmannians and partial flag varieties, at least I think the Grassmannian is like the smaller example, and you have many Grassmannians inside a partial flag variety. But here we actually turn things around and we can see how the cluster algebras of partial flag varieties are cluster subalgebras of the cluster algebra of a Grassmannian. Right? And as people like to work with Grassmannian cluster algebras, and they are still a bit easier than partial flag varieties or their cluster algebras, this is a desirable result to have. Okay, so before getting to that result, let me tell you what partial flag varieties are. So instead of, it's in the Grassmannian, we always just have points being in correspondence with subvector spaces of a fixed dimension. Here we fix a tuple of dimensions, d1 to dk, between 1 and n, and we consider a flag of vector subspaces, containment, so a vector space contained in each other, and the dimensions of every vector space in my flag should be the ones I prescribed. Now, very similar to the case of Grassmannians, I can represent points in the flag variety or partial flag variety by matrices. And now, instead of just choosing one basis for my one vector space in the Grassmannian, I have to choose bases for every step in the flag. But as my vector spaces are contained in each other, well, I choose the bases compatibly. So I choose a basis for the first vector space, great, and I add some more vectors to the basis to have a one for the second vector space, and so on. So the first di rows in my matrix should then span the ith vector space in my flag. Okay? So I get a dk times n matrix. And now again, I forgot my convention on Grassmannians. If it was columns instead of rows, I'm sorry. If you find those in the slides, let me know. I'll try to fix everything and make it compatible. But yeah, so great. So for my flag, I pass to a matrix. And again, of course, there's a choice involved. There's many choices involved to choosing the bases. So one matrix, one vector space, but one flag is represented by several matrices, and there's GL actions relating them. And then I also have Plucker coordinates. I define them in the same way as before, determinants of these matrices. Now just one small difference is that I have Plucker coordinates whose index sets have different cardinalities. So for every di in my tuple, I have Plucker coordinates of the corresponding size. Right now, I'm not interested in only maximal minors of my matrix, but all these minors. So here's an example. If this is my matrix, so my vector space, I didn't even say what's the flag. That's funny, yeah. So this could be any flag, 1, 2, 3, or just 1, 2, or just 2, or just the Grassmannian. In C4 or K4, yeah, then P1, 3, 4, well, it picks out 1, 3, and 4 as columns and computes the determinant. Okay, so the Plucker coordinates also here, they satisfy Plucker relations. First of all, the same Plucker relations that we saw for the Grassmannian hold here as well, if I only focus on Plucker coordinates on one fixed size. But now I also have relations relating Plucker coordinates of different sizes. Right, so I have lots of identities among these minors, and I need to use all of them to define an ideal for the flag variety. And I get an embedding of the flag variety by passing first an embedding into a product of Grassmannians, just sending every vector space in the flag to the corresponding Grassmannian, and then I compose that with the Plucker embeddings we've seen for the Grassmannian, right? So this gives me a Plucker embedding of the flag variety, not into one projective space, but a product of projective space. And this is the notation I will be using for the homogeneous coordinate ring with respect to this embedding. And wants to take note. No one's
It's
right.
partial because it's not partial if di plus 1 minus 1 is di.
Yeah, exactly. Yeah, it's called the full flag variety or just flag variety if all the integers between 1 and n minus 1 appear.
Oh, okay, n minus 1.
Yeah, like all of it. And yeah, it's called the Grassmannian if k is 1. Yeah. Those are the two extreme cases, right? I can have all the dimensions in between or just one. Okay. Great. So partial flag varieties have admit a cluster structure. This homogeneous coordinate ring is a cluster algebra. This result has been proved by Geis, Leclerc, and Schröer, based on results of Bernstein, Fomin, Lewinsky before, and it's been extended to more general flag varieties recently, and I forgot the name, a student of Milan Yakimov. I'm sorry, ask me for the reference and I'll find it if you want to know the latest point of view on this. And there's a nice combinatorial construction how to get an initial seed here as well. It goes in 3 steps. I don't have all exact details on the slides, but I'll walk you through a sufficiently large example to have a feeling of what we're doing. So the 3 steps are the following. There's a permutation associated to a partial flag variety, and that is this one. So for D1 to decay, yes, D1 to decay are my integers. I start with dk plus 1, dk plus 2, and so on, and run all the way until n, and then I go to dk minus 1, at 1, at 2, and so on until decay. So it's like this derangement, but instead, so in the Grassmannian, we saw this permutation, we just had 2 consecutive intervals in the image, and here we have 1 block for each di. Right, and we go, well, the last one is 1 until d1. So we will draw a wiring diagram, a graphical presentation of this permutation, specific one, that's the first step. Then we're going to associate a quiver to this picture by taking the dual graph. Faces in this diagram will be vertices in the quiver, and there's a way to put arrows between faces. And then last one, we're going to take care of how to associate cluster variables or like elements in this homogeneous coordinate ring. They would all be in terms of Plücke coordinates, but not only Plücke coordinates. So here's the example. Can you see? Okay, if you're having trouble to see the indices from the back of the room, I invite you to come closer. Or take a picture. If your phone is really good, take a picture and zoom in. That might also work. Okay, so what am I doing here? Well, down here I have the numbers 1 to n. N is 7. My di's are 2 and 5. And I'm going to draw this permutation. So here's the images of the permutation. Sigma 1 is up here. Sigma 2 is here. These are also just ordered 1 to 7. But I've associated each of them with the pre-image under the permutation. And then I connect. So 6 is the image of 1. I connect a line from down here up here. 7 is the image of 2, and so on. And I'm going to do that so that within one interval between 1 to D1, these lines don't intersect. And then 3 to 5 is my next interval according to my choice of DIs. All these lines also, they don't intersect. Right? They just go directly to their images 3, 4, 5. And then the same for the last interval, dk plus 1 until n. And great, so now I have a graph. I have plenty of bounded regions inside this graph, and all of those will correspond to mutable vertices in my quiver. And then I have unbounded regions here on the left, and those will correspond to frozen vertices of my quiver. And then additionally, I will add vertices for the di's I have. So 2 were the di, so I add up here a vertex that I call omega 2. And 5 was the di, so I add omega 5 here. And then if you ignore these extra vertices, there's 3 types of arrows you can observe in this graph. So if we focus, for example, on this face that I've labeled 2, 3, 4, 5, and I'll tell you why it's labeled like that in a second. What are my arrows? Well, they're perpendicular to the line segments that I see from left to right, from top to bottom, and diagonally from bottom right to upper left, going through a crossing of lines. Okay, so if a face in the interior shares an edge with another face, there's an arrow passing through it. And if they share a vertex, there's an arrow passing through it. And then I have these 2 extra vertices that are, there's a precise rule to which other vertices they are related. And it depends on exactly where the line is that it corresponds to. So for example, here, I have this face on the left of the line 2 and this face on the right of the line 2, and these 2 will form a triangle with the extra vertex. If you want to actually know the details, I'm happy to just share the paper or tell me. Okay, so great. So this is a quiver I can associate with this permutation. And the indices I've drawn here correspond to the indices of lines, read from below, that are on the northeast of my face. Right, so for example, this phase 2 is only below the line labeled 2, and so it only gets the index label 2. And then, yeah, this 1, 4, 5 has 2 lines passing northeast, lines 4 and 5. Okay. Any questions on the combinatorics? Okay. Great. So these index sets that I've drawn here, in fact, already correspond to cluster variables. And they are to be understood as minors or generalized minors for other types of an upper triangular unimodular matrix. And the way to take them is like the index set I have would be my row set of the minor, and the column set is bound to n. So it's an interval from n minus the cardinality of my, well, the right cardinality. Right, okay. So the minors are solid to the right of my matrix, right? The last, you always pick the last many columns, as many as you need. That makes sense, I'm sorry. So it's hard for me to describe in words. Okay, great. So I told you there's a way to express them in terms of Plücke coordinates, and that's just very linear algebra 1 calculation of Laplace expansion. So Plücke coordinates, I defined them to be index sets where my row set always starts at 1 and ends at the corresponding cardinality, and my column set varies. So all I have to do here is pass from the minors whose column sets are bound to n, like intervals are running up until n, and row sets vary, expressing them in terms of minors corresponding to Plücke coordinates. Yeah, and this is the Laplace formula that you have to compute if you want to do that. We have one extra bonus nice ingredient here, and that's the observation that all the index sets that appear here are unions of 2 intervals. 1 interval or unions of 2, that there's no more complex index sets appearing. So here, for example, 2, 4, 5, we have the interval that just contains 2 and the one that contains 4, 5. Or here 1, 2 and 4, 5, and then, yeah, here's complete intervals, 1, 2, 2, 5, and so on. Okay, so it's not as bad. So we compute this Laplace expansion, we get an expression in Plücke coordinates. All of these minors turn out to be either quadratic in Plücke coordinates or on the nose of Plücke coordinates. And there's a combinatorial tool that we can use here to associate to each cluster variable a tableau. And the tableau we will associate will correspond to one of the terms on the right-hand side here. And it will be filled by the index sets that appear. And there's an order on tableau, so every monomial here corresponds to one tableau, and an order on tableau allows us to choose the maximum one. So if I do that in my example, this is what I get. Whenever you see just one column, this is just a Plücke coordinate. And when you see 2 columns, this is a quadratic expression in Plücke coordinates.
Sorry, could you mention the Plücke coordinates of what matrix and the minors of what matrix? Is the same matrix?
Yes, the same matrix, same matrix. So think about you can think of the flag variety as a quotient of SLN modulo a corresponding parabolic subgroup. So we have orbits in SLN, and we take representative matrices in SLN. And in fact, there's one more step how we can simplify our life, only thinking about unimodular upper triangular matrices. So matrices that have 1 along the diagonal and then upper triangular entries, certain entries. Some of them still 0, but yeah, so there's an open embedding. But this is an affine chart to the flag variety matrices of this form. And the calculation takes place there. I'm happy to give you details on what these matrices are.
the sizes of the glucose or of the minors? I mean,
The sizes of
the sizes of the submatrices that you're computing, the determinant.
yeah, so okay, so yeah, these are dk times n matrices. But if I want to think of the flag variety as a quotient of SLN, so n times n matrices, yeah, this you can think of these as being embedded in there just by having certain extra rows that I don't care about. So yeah, it's a slightly different approach to get the flag variety as a quotient of SLN, but like both are valid representations of elements. You can also take this matrix and just extend it to an n times n matrix by adding standard basis rows, just corresponding to standard basis vectors, thinking about k to the n as being part of your flag. Like if I extend the basis I chose until vk to k to the n, then I get an n times n matrix. But the minors I'm interested in will be always focusing on this submatrix.
And the glucose that's
Yeah, they're always in the submatrix. Yeah, I will never have any in here. I will never have any indices appearing that are larger than dk. Sorry, that are no, sorry, that's not the reason. The reason is that I always choose the row set from 1 to dk, and the column set is what varies over my Plucker. Okay. And yeah, so these I have to consider them as minors of the full n times n matrix. And yeah, then I get this translation expressing them in terms of Plucker coordinates. Okay, and then I use this trick to just give you combinatorial datum for every Plucker coordinate, but there's also a character formula given a tableau that will actually compute the expression back for you. So it's a very nice combinatorial gadget that we can use here. Okay. And yeah, I put it on the slide so I didn't mention why we have this association with tableau actually goes through a whole bunch of theory on representation theory of quantum groups. And these tableaux more generally represent elements of Lustig's dual canonical basis for the quantum group. And cluster variables happen to be part of this basis, so we have this tool. But not all kinds of tableau I could write down would correspond to cluster variables. And yeah, I don't know if John Rong is here. He's expert. I think hopefully will come later. So when you have any questions on how and why it's possible to relate tableau to cluster variables, I will forward the questions to John Rong, lovingly. Okay. Great. So let's get back, or let's remember. I wanted to go to this point of having cluster algebra embeddings. So how do we do that here? Well, we talked about the flag variety. The Plucker coordinates I denoted them with capital Pi. And I'm going to consider for a given flag variety with indices d1 to dk in k to the n. I'm going to go to a Grassmannian that remembers dk, the largest dimension in my vector. And capital N is the difference of, is what I need to fill up from d1 to dk. So it's n plus dk minus d1. And the Plucker coordinates for my Grassmannian were lowercase p's. So here's a map that I can define on the Plucker coordinates very naively. If I have a Plucker coordinate in the flag that is not of size dk, well, I can just fill it up to be of size dk by adding the indices n plus 1 until n plus dk minus the cardinality I already had. And this defines an embedding, or you can check, it defines an embedding of these algebras. So Plucker relations I have here, hold here, and kernel is 0. But the surprising thing here is that it's also an embedding of cluster algebras. So what that means is there exists a seed in the Grassmannian whose quiver, or that has as a restricted seed, a seed for the flag variety. Right, so I find a quiver inside the Grassmannian cluster algebra, so that when I freeze and delete some vertices, I see the quiver of the flag varieties. And the cluster variables at the vertices correspond to the images of the cluster variables of the flag under this map. Okay. So yeah, this was a kind of surprising result from the math point of view. In fact, the inspiration came from physics intuition of how certain kinematic spaces are related. So let me pause here, because then the rest of the talk will be relating partial flag varieties to the momentum twister variables and spinor helicity variables that we've seen pop up in other talks. Is there any question on this result? Right, so the proof here really is just showing this existence of a restricted seed by giving a mutation sequence from the initial seed of the Grassmannian to that seed.
Do you have any combinatorial interpretation of the scene?
For the Grassmannian, no, actually it does not come from a Plavic graph, which cannot, because I know that I have these quadratic cluster variables here, so I have to go out of the Plavic graph world in the Grassmannian to get there. Yeah, no, it's actually I have a student working on this, trying to exhibit other mutation sequence or trying to find other seeds that have the same property, or also changing this embedding a bit. I mean, we made a choice here of how to make all small Pulchers and how to turn them into Grassmannian Pulcher coordinates. You might as well choose a different index set to fill up here, like any indices from n+1 to capital N are, up for choice. So yeah, very few is known.
I was wondering how this is reflecting the symmetry of the flag variety and the Grassmannian, because this flag variety is a cyclic symmetry. But then if you insert between 1 and n these extra indices, it does seem that it does not. It kind of breaks this cyclic symmetry.
Yeah.
So how can you comment on that?
Yeah. It breaks the symmetry. I don't have any intuition of.
What's the interpretation of the cyclic symmetry and the flag variety if you embed under this embedding? It does seem not very natural.
To see.
I mean, the cyclic symmetry is not only in the Grassmannian, but also it descends also on the cluster algebra. There is a cyclic map that you can apply in the cluster algebra. And then that means that your image of this under this map is something, but it doesn't descend on the cyclic symmetry of the image Grassmannian. Something else. I mean, if you cyclic shift the labels from 1 to n.
Yeah.
But then if you insert everything.
Yeah, and then you do the map. Yes, I don't know. I mean, this is not much has been explored in this direction yet.
Okay.
And it would also, yeah. I mean, there's.
I'm also wondering from a physics point of view. I mean, from 1 to n, their interpretation of like some ordering of particles. But then if you insert randomly certain number of things between particle 1 and n. Then you break the entire symmetry.
Yes.
And then why do you expect this is something nice or canonical? Or
yeah, I mean, this happens when you break the dual conformist symmetry, right? This is the is the physics.
Yeah, no, exactly. I mean, I understand it could be relevant, but then it's like adding the infinity twister, saying that the infinity twister lies between like 1 and n, but why not?
True.
Like, there's no difference.
No. This is okay. This is also why we have to take this symmetry into account when we want to get back to the physics. We have to get rid of this choice and go through all the possibilities of adding the infinity twist in different places.
Okay, so you have to prove it.
Yes, yeah, we do have to prove it. But this, like the math result so far is just here, because then.
I was asking independent from physics about symmetry and flag variety, how that descends into imagine this map, since the map seems to break it.
Yeah. I don't know. It would be great to find out.
Okay.
Oh yeah, this is a project for Graphs, and all these questions. If there's students here that would like to explore cluster algebra structures and flag varieties Grassmannian, there's plenty of things to do. Okay, so in my last 5 minutes, let me get to the where to find partial flag varieties in physics and in scattering amplitudes. I feel like this slide is like a way more simplified version of what we saw by Rowan yesterday. I think at this point it would be good to insert Rowan's talk. Actually, you want to take over?
It was exactly 5 minutes.
Yeah. So this is my simplified point of view on things. If there's questions, I'll refer you to the physicists. Right. So we have scattering amplitudes. We've seen them. For those who don't know, I didn't know, you can typically express them as generalized polylogs and express them as iterated integrals. And once you have such an expression of an iterated integral, you can read off the symbol. So this integral would correspond to reading off the arguments of the d logs. And forgetting about the rest. So it's a great way to kind of condense information. We lose the coefficients, but we still have lots of information kept. And these, the elements appearing in the symbol are called the letters. The symbol itself, you can think of it as a word in the symbol alphabet. And this has led to the bootstrap that Rowan mentioned yesterday. So first, there was an observation by Mark and collaborators that in the Grassmannian 4.6 and 4.7 cluster variables of the cluster algebra predict the symbol alphabet. They coincide. And then the bootstrap program is the following. If you want to bootstrap the amplitude, you're going to guess what the symbol alphabet is. You're going to think of the amplitude as a polylogarithmic function on the kinematic space. So in this case, it was the Grassmannian. And then you search the space for functions that have the corresponding symbol letters given by cluster variables. Rough idea. Physicists, don't take me too seriously and correct me if I say something that is far too simplified. And here's a long list of references. So this has been very fruitful. Lance Dixon has pushed this program a lot. So you'll see his name appearing here, but also Rowan's advisor, James Drummond, Omer Durgudan, and like many others. So there's progress in different directions. The references I have go until 7 points in n equals 4 super units. And a natural question to ask is, okay, what happens if we leave this very nice n equals 4 super units world? And we can do that by extending to non-planar cases or to non-dual conformal cases, for example. What are the kinematic spaces and what can the cluster algebras and the cluster variables tell us about the symbol alphabets? So here's the momentum twistor parametrization that we've seen before. This is in the dual conformal invariant setting, where we have n particles. We pass to their momentum twistors in CP3, and parameterize the kinematic space by taking determinant. So I interpret my points in CP3 as giving me the columns of a matrix, and I take the determinants of these matrix. And well, they satisfy Plucker relations, and I recover the Grassmannian 4n up to column scaling. So it's actually the conformal the point configuration space. And I can also extend this approach to the non-dual conformal setting, as what Matteo referred to, and also Rowan mentioned this. So if I want to get rid of conformal symmetry, what I do is I add one extra infinity twister. And how that manifests in this interpretation is introducing 2 extra points to my tuple of n points in CP3. And then I parameterize everything by still considering the minors I considered before. They run until so these are these maximum minors up until the nth column of my matrix. And then I add these extra angle brackets, just depending on 2 indices from 1 to n, where I always take these extra n+1 and n+2 point together, right? So the whole system now depends on the choice of points, or if I compute the minors, it depends on the choice of points I have from 1 to n, and the line generated by n+1 and n+2, right? So there's no individual dependence on the n+1 and the n+2, just the line they generate. And the space I get, I can consider it inside of the Grassmannian for n+2, or again, quotient by C star to the n plus 2. And this is called the momentum twistor variety. Okay, great. So at this point, you might already guess how it's related to partial flag varieties. Well, here's a map. These 4 angle brackets, I mean, this minors of a matrix, we just on the nose identify it with the Plucker coordinates of index set cardinality 4. And the 2 angle brackets, we identify it with Plucker coordinates of cardinality 2. And this map, in fact, induces an isomorphism between the momentum twistor variety and the quotient of a partial flag variety. Yeah, so, and the partial flag variety I can identify with is the one 2, 4n. And this identification has led to some observations regarding the symbol letter. So in case of n equals 4, the partial flag variety is of finite type. So we have a finite set of cluster variables. And if we take all of these cluster variables and we complete with respect to the symmetry that I had on the flag, and take all the permutation copies of the cluster variables, we do recover all but one symbol of in the corresponding alphabet. And this one symbol that we're missing is W31, for the ones that know this notation, is one where there's still ongoing discussions if it's actually a relevant element of the alphabet or not. And in the case n equals 5, very recently there's been very interesting progress by, I think, 2 groups of people. So first of all, here something significantly changes from the point of view of partial flag varieties or cluster algebras, because we pass to affine type. So we have an infinite collection of cluster variables. Can no longer hope to get to observe what we did in n equals 4, because there's infinite many cluster variables in the symbol alphabet. Up to a certain loop level is always going to be a finite set. But there's been some progress by Mark and Anastasia and their postdoc and their student Wang was here. Yes. On computing a certain set of cluster variables. I don't understand yet how they decide what are the cluster variables that are relevant or not. Again, permutation completing, and they make a similar observation that they recover all but some symbol letters. Again, not clear what happens to the letters that are not there, if they're really relevant. Also not clear how to generalize, how to predict which are the cluster variables that are relevant to be part of the symbol alphabet. So very interesting questions in that direction. Very curious to see where that leads. And then there's results by what Rowan reported yesterday with James and Omer. Correct me, both groups, please correct me on anything that I'm reporting on here. That observed that also cluster adjacencies play a role. So exactly like in which orders letters can appear in words. These rules are also partially, completely, I don't know, there's some way the cluster structure predicts some of these rules. Okay, I'm already over time. I don't know if I get like 1 more minute. Yeah. Okay, great. Okay, great. So this is the case of the momentum twistor variety, but in fact, we can also see partial flag varieties in the spinalicity parametrization. So this is also something we've seen already yesterday, I think in Mark's talk and in Nima's talk. We can pass from a configuration of n light-like particles to their spinahelicities. So if I start with n particles, this is just parametrization, right? We go from a 4-vector to a 2x2 matrix, and that 2x2 matrix is of rank 1, so it factors as lambda, lambda tilde. Their product being 0 because that's p squared, and the mass, I'm assuming massless. So I get 2 times n matrices, whose product is 0. And the spinahelicity variety is just the space of all these pairs of 2 by n matrices of full rank, such that their product is 0. I can parameterize it by the 2x2 minors of these matrices. So I get minors Pij and Pij tilde for the 2 corresponding sets of matrices. And I identify Schouten identities, which are Plucker relations independently for the 2 sets and momentum conservation. And here I can also pass, I also have a map from a partial flag variety to the spin helicity variety. Right, so spin helicity variety is this space. What's the map? Well, the Pluko coordinates, Pij, just identify them with Pluko coordinates in the flag variety. And for the others, the Pij tildes, I pass to Pluko coordinates of opposite cardinality n-2, and there's a sign that I introduce. So this n minus ij is taking 1 to n, and the complement of I and j. And if I do that, the Pluko relations I had before translate directly to Pluko relations, and momentum conservation translates into mixed Pluko relations between the two sets of minors. And yeah, this gives me an isomorphism between these spaces. And I should mention also work of Yasin and Anel and Bernd that study more generalized spin helicity varieties, leaving this space motivated by the physics, but they add another parameter where the matrices lambda lambda tilde can now be of size k times n, and they show that these two spaces have the same dimension. So in this case, we get an isomorphism.
Just a comment. So geometrically, the momentum conservation is telling that lambda is included in lambda tilde perp, where lambda tilde perp is the plane perpendicular to lambda tilde. So then you have the flag that you're considering is lambda together with lambda tilde perp, like the pairs of planes, and that gives you the true set variety.
Yes.
And that's the plukers that you're defining are the plukers of the perp.
Yes.
Yeah.
Yes.
Okay, no, it's like geometrically maybe it's
Okay. Yeah. Great. Yes. Absolutely. Thank you. Yeah. Yeah. Okay. That's it. Thank you.